Thank you for watching my presentation. I'm going to present you my study, how sonification of heart rate variability can entrain bodies in motion. Music has an undeniable effect in our lives. It affects our movement, our vitality, and our emotions. It makes us move while it is created out of movement and its consequential oscillations. Studying how music impacts our movement, how dance affects our inner and interpole interaction, and how the sonification of pole information affects the quality of our movement is of great interest in our scientific community. In a previous study presented in MOCO'19, the outcomes of which will be recalled later, we investigated the effect of music in walking when participants were exposed to songs of different rhythmicity. In this work, we expand our previous study to investigate the effect of music in dance and further the effect of music in our movement when music is enhanced by bodily information and specifically of our heart rate. Two experienced salsa dancers, a male and a female, participated in our study. We use inertia measurement units to record the linear acceleration of 6 body parts for each dancer and the ECG cable extension of the EEG system in Obio to record the heart activity of the female dancer only. We designed an interface which streams the ECG signal to a Python interface via the lab streaming layer. The Python interface analyzes the signal in real time to extract the heart rate. This information is then sent to Mach7, where the speed of the song is adapted to the continuously updated heart rate. Finally, we save the ECG and audio signals, which are synchronously recorded, and the linear acceleration of each body part. In our study, we have two baseline conditions. In the first one, the dancers danced an improvised social dance piece, and on the second one, they rehearsed a well-practiced choreography. In both cases, the songs were played in their original tempo. Then, for each baseline condition, participants re-danced the pieces twice while listening to the heart-adapted songs, formulating alteration 1 and 2. The altered versions of the songs had different durations depending on the heart rate of the female dancer during the dance. The data structure used to analyze the signal was the micromovement. To do that, for each signal, we got the raw data, we mean-shifted them, detected the peaks, and then normalized the peaks based on the local minima using this function to finally estimate the micromovements. For each peak, we maintain the normalized amplitude and its interpeak interval to investigate the temporal and spatial features of the signal. Here, we see the figures exported in the process of building the micromovement data structure from its type of signal. At this point, I would like to emphasize that the reason we studied the audio signal is that it includes the information of the heart adaptations which we are interested to study. One of the tools used to evaluate our data was the estimation of the gamma signatures and the meaning of their location on the gamma plane. To estimate the signatures, we built the histograms, probability density functions, and finally we extracted the gamma distribution signatures, which are the shape and the scale parameters presented here. The empirically informed interpretation of this plane is that signatures of distributions that belong in the left upper quadrant are more random and memoryless, whereas signatures that are in the right lower quadrant belong to distributions that are more symmetric and systematic. To examine the heart-music relation, we first estimate the gamma signatures of the heart micromovements. Column A and B show what happens during the improvised and the routine dance. Its marker color corresponds to a different main condition. Due to the nature of the two main tasks, we expected to see more adaptation and learning in the improvised condition comparing to the previously learned routine. So let's see what happens in the result. Observing the black edge markers, we see that the condition where the dancers improvised has a bigger initial shift away from the response to the original music in both alterations, whereas shifts are smaller in routine condition and more obvious in alteration 2. This outcome shows that there are bigger learning shifts during the improvised dance. Then we estimate the gamma signatures of the corresponding audio data. Here, it is interesting to observe the impact of the natural heart signal to the artificial audio signal and how the changes of the heart signatures have impacted the audio gamma signatures. The body is the medium of the interaction between the heart and the song. It adapts to the heart-based music but also affects the heart activity through its motions. Examining how this closed-loop interaction impacts the body is the next goal of this work. The figure displays the gamma stochastic signatures of the acceleration macromovement of the two tasks for the female and male dancer. The location of the signature shows that the female dancer has slightly more symmetric and systematic motor behaviors. This contradicts the fact that in social dancing, the male dancer is the one that leads the dance. To study the inner and intercorrelation of the two bodies, we estimated the autocorrelation of each body part and the cross-correlation across the body parts of the two bodies. Here, we see the color maps of the estimated autocorrelation for each body part for all conditions. The top 6 rows correspond to the body parts of the male dancer and the bottom 6 to the female dancer. To better translate the information that these matrices include, we estimated the sum of max, mean, and average autocorrelation of all body parts for each dancer. In most figures, we see that the yellow bars are taller than the blue bars, which means that the female dancer has higher sum of autocorrelation, and based on figure D, she performs the best when dancing the original song of the routine. Finally, we identify the body part that has the maximum autocorrelation in each condition. It is interesting to note that the female dancer has max autocorrelation on the left ankle in 5 out of 6 conditions, and the female dancer has max autocorrelation on the right ankle in the same frequency. We apply the similar approach to the cross-correlation analysis. In this case, we study the cross-correlation across the body parts of the male and the female body and across the body parts of the two bodies, which we name together and we notated as T. We estimated the max average and the max anti-cross-correlation or else mean cross-correlation. Figure B indicates that the female and the male dancer, yellow and blue bars, have almost equal max cross-correlation in all conditions, and that their together black bar performs the best in the last alteration. In figure D, we observe that the female dancer has higher cross-correlation values when performs the routine in its original form. Also, the best together performance is reached during the same condition. Finally, we located the pair of body parts which had the max cross-correlation in each condition, and we found that the female dancer has max cross-correlation on the left and right ankle in 3 out of 6 conditions. The male dancer has max cross-correlation in the pairs of left and right wrist in 3 out of 6 conditions, and the two bodies have max cross-correlation on the pair on left and right wrist in 4 out of 6 conditions. Here we see the color maps of the Kolmogorov-Smirnov test applied on the amplitude and the interpeak intervals of the linear acceleration micromovement of the female and male dancer across all possible condition combinations. In this figure, red cells indicate higher differentiation between the empirical distributions. Therefore, the female dancer whose heart signal was used for the audio augmentation appears to be more sensitive to the adaptation process, comparing to the male dancer. It is also important to notice that there is no pattern differentiating the outcomes of the amplitude to this of the inner peak intervals. At this point, I would like to recall the results of the previous work for discussion. In this figure, the dark blue cells show higher differentiation between the empirical distributions. The results of the previous work indicate that while different forms of music may affect the temporal features of the linear speed of the head, torso, arm, and heart activity, they did not consistently impact the amplitude of the signals. Unlike in rhythmic walking of our prior work, in salsa dancing, the technique, the experience, and the expression seem to have a higher impact on the volume of the movement dynamics. Indeed, the present study reveals modulations of the spatial components of the motion that were absent from the walking study. In this sense, dancing to the musical heartbeat differs from merely walking.